Hello, everyone. Welcome to today's live broadcast, Reference Architectures for the QIAGEN Biomedical Genomics Solution. I'm Julianne Tide of Libraries, and I'll be your moderator for today's event. We have a few important announcements before we begin. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit questions by typing them in the Q&A box, which can be found by clicking on the green Q&A button at the lower left of the presentation window. We'll try to answer as many questions as we can. You can enlarge the slide window by clicking on the screen icon on the lower right-hand corner of the slide window. If you have any technical problems viewing or hearing this presentation, please click on the support button at the top right of your presentation window, or submit your problems to the green Q&A button at the lower left. Today's webinar is being sponsored by QIAGEN. Please get more information at QIAGEN.com, and it is also being sponsored by Intel, INTEL.com. I would now like to introduce today's speaker, Michael McManus and Mikhail Flensborg. Dr. McManus has a 30-year history in scientific software and hardware marketing roles, ranging from R&D to sales, including business development, marketing, project management, and executive management. He currently acts as a senior health and life science solutions architect at Intel. He is part of Intel's effort to promote the use of modern computational solutions in healthcare and life science markets. Michael Flensborg is the Director and Solutions Lead for QIAGEN Bioinformatics High-Volume Sequencing Solutions in Aarhus, Denmark. He has served over 30 years of combined experience in the software industry with specialties in bioinformatics software, architecture, service to developer kit. Mr. Flensborg has been instrumental in building strategic alliances and research collaborations for QIAGEN Bioinformatics. I will now turn it over to Dr. Michael McManus and Dr. Mikhail Flensborg for their presentation.
Thank you. So, welcome everybody, and welcome to today's webinar on reference architectures for the QIAGEN Biomedical Genomics Solution in collaboration with Intel. We're very excited about that because we always get questions from customers about they have a specific need, specific sequencing throughput, and what kind of hardware architecture do they actually need to be able to analyze this throughput. So I'm, as introduced, Michael Flensborg. I've been, originally I was part of CSE Bio that was acquired by QIAGEN 3 years ago, and I've been with CSE Bio since early days, so I actually have 11 years of experience in this field. As mentioned, we are now in QIAGEN Bioinformatics, and to give a little overview about what that is, we have this information here, and it's actually a formation of 3 companies, namely, as I mentioned, CSE Bio, that I'm from, and Ingenuity Systems and Biobase, and together we are actually the biggest bioinformatics company in the world, and we have 120,000 users worldwide, and 40 of the top 40 pharma companies rely on our bioinformatics solutions. We also have more than 30,000 publications referenced in QIAGEN Bioinformatics, and more than 420,000 sequence samples uploaded into our secure and private Ingenuity cloud. To give a little introduction to what we are going to talk about today, I would like to mention that our tagline in QIAGEN is from sample to insight, meaning that we have a unique technology for every step in the, you can say, the universal NGS workflow, from sample to insight, all the way from sample isolation to actually the actionable insight that you would need. And what we are going to focus on today here is what we call the secondary analysis, which is analyzing the data loaded off the sequencing instruments. That is the most compute-intensive part of the workflow, and thus also the part of the workflow that requires most compute resources. So that's where it's actually relevant to talk about what kind of compute infrastructure do you actually need to be able to accomplish this. Also, I would like to give a little overview of what we're actually talking about here, a software solution that we provide from QIAGEN Bioinformatics. It consists of primarily two products, and the primary product that is very widespread in the market is called CLC Workbench, and in terms of CLC Genomics Workbench and CLC Biomedical Workbench, and that is a desktop computer software that you install on your laptop or your desktop computer, and then you are able to analyze data coming from the sequencer. And it is well known in the market to be extremely user friendly with a graphical user interface that computational biologists like and biologists like, and also biomedical experts. It's very easy to use, and it's drag and drop, and it's Windows, and it's in general a nice user experience to use. And then on the other hand, we have the challenge of analyzing these large amounts of data. And if we are talking data of a certain capacity, then a desktop computer is not anymore sufficient for doing this analysis, even though you theoretically could do it with the interface. So that's why you bring high performance computing into the picture. And here we are talking computer clusters and server side architectures that resides in typically in the cooling room, maybe in the basement or another room, or sometimes even on another site. And that is in general a very complicated area that traditionally requires a lot of computing skill and a lot of IT expertise, and in general for a scientist or a biomedical expert is very difficult to understand, and it certainly is very difficult to handle. So that's why we have had success with masking the complexity of cluster computing by adding the CLC Genomics Server software, which you can install on your cluster architecture or your server architecture. And the good thing about this is that, seen from the end user perspective, that the user-friendly end user perspective that the scientists like, there's absolutely no difference in working with the data and accomplishing what you actually want to accomplish. So it's a matter of instead of executing a task or analysis task directly on your desktop, then with the user-friendly user interface, you simply submit the task to the compute cluster environment, whereby it's then scheduled for execution, and he's gonna get a notification when the job is done. I will come back to that in a little bit. So to be a little technical, we have to be that here to explain what it's all about. We have this small diagram of how it actually works. So how it works is that when you schedule a workflow through the workbench to a compute cluster, then it's scheduled for what is called distributed resource management. And that means that there is a central scheduling mechanism where you can that takes the whole workflow and puts it into the mechanism, and then it is distributed to a compute resource. And what I mean by compute resource is that a compute cluster is typically an array of what we call compute nodes, which is individual computers. And from a scheduling point of view, then it's a matter of finding an available resource in that compute cluster, and then taking the components in the workflow and schedule them for execution on each of these available nodes. And if all nodes are busy doing tasks, then it's put in a queue for later execution. So that means that, seen from an end user point of view, it's just a matter of submitting the workflow to the scheduling mechanism, and then they know that it will be executed eventually when it reaches its point in the queue. There's two ways to schedule that I'll not come into detail with here and now, and that is called job nodes and grid node scheduling. And there are some differences, primarily regarding using external grid scheduling systems. I would like to explain a little bit about how an organization actually uses this system. And as you see up in the top, we have the end users that use the workbench, and that's the user experience that they like, and that's what they can do. Remember that very often end users, scientists, biological scientists, biomedical experts do not have the deep, mature IT skills that can make them handle command line tools, Linux tools on a compute cluster. So that's what they can use. And then in the middle, we have the CLC server, the genomic server, that they then submit jobs to. And of course, we also have an IT administrator into the picture that makes sure that the system is running, etc. And then on the other side, we have the computational biologists also, and they're typically called bioinformaticians. And very oftenly, and actually also historically, the bioinformaticians has been the staff that you can say owned the resource, the analysis resource. So they have been historically, and also many places still, they are serving as user interface towards the end users in terms of operating the analysis engine. And that has historically, and we have heard very often stories from organizations that there is a conflict between the end users and the bioinformaticians, for that simple reason that the bioinformaticians is a very limited resource. And that when they serve as a user interface towards the analysis system, then they become even more a bottleneck, because the end users come all the time with requests for doing different kinds of analysis that could be BLAST or mapping or variant calling, etc. And they end up spending all their time on serving the end users instead of actually doing bioinformatics. So, and seen from the end user point of view, that can create some conflicts, because this limited resource that never has time and is always busy, and seen from a bioinformatics point of view, it can be the bothering end users that comes with stupid questions and stupid requests all the time, and thereby there is a built-in conflict. So that's what we have had success with in QIAGEN Bioinformatics, is actually resolving this conflict and make everybody good friends. So with our customization abilities on the system, command line tools, first of all, I would like to mention, which gives the same abilities towards the system in terms of scheduling and administration, data administration, as from an end user point of view, but with a command line tool as interface. And even more importantly, I would also like to mention that we have external applications integrations also sitting on that side. So that means that, seen from a bioinformatician's point of view, you can deploy other tools and external tools. That could be from many of the good tools from the open source environment. There could also be tools that they have developed themselves. They can be deployed into the system, and by specifying in the system how the parameters work, it is then translated automatically into a user interface that the end user can actually use and submit jobs with themselves. So that means that it will be easier to plan your day as a bioinformatician, because you can actually choose deliberately when you want tools to be available for the end users, and you do not have to be bothered every time an end user come and ask for requests for analysis. I would also like to mention, as part of the system, we have a data management layer which means that the data is, of course, on the server side stored centrally and available to all end users and also to bioinformatics staff. And there is traditional permissions and access privilege mechanisms around that in terms of who can read and who can write and who can view the data. And these data are normally stored in a file system, but can also be stored in a database. Now I would like to move on to talking a little bit about the optimizations we have done for the Intel chipset and also together with Intel. So we are very well known not only for doing very user-friendly software, we also well known for doing very high-performant software. And there are various optimizations behind it that I would like to mention. One is that we are using an Intel technology called SIMD. It stands for Single Instruction Multiple Data, which actually means that not only is the software, of course, you can say multi-threaded to run on available cores on a computer processor, but using this technology, it actually also makes it possible to run a single instruction on multiple data. So that's if you regard data as multiple data, that could be a vector of 16 numbers, then these 16 numbers can be processed in a single instruction on a single core at the time. So that's one example of how we have optimized, and this is being done in some of our most essential and most compute-intensive tools, and is implemented in machine code. I would also like to mention recently we have done various enterprise-level optimizations together with Intel. So in the fall, we published a white paper around that we took focus on the absolute highest throughput that is known, which comes from the Alumina HiSeq X10, which is up to 18,000 whole genomes per year. And we tested this with the throughput that is needed at highest capacity, and we set ourselves the challenge of trying to analyze the data at that speed that it can actually be produced. And we showed with a system that is described with this white paper that not only can we do this with a system of 32 compute nodes, but also that the system is extremely scalable, linear scalable, that it actually scales up linearly to the data demanded to be analyzed. So what we specifically tested is that we had the test setup simulating a HiSeq X10 throughput, which is 18,000 whole genomes per year. And with that, we had to solve that with that given workflow, a variant calling workflow, we had 32 compute nodes running in parallel. And with this setup, it was possible to analyze one whole human genome every 30 minutes in average, which means 48 whole genomes per day. And we also made some tests on whole exomes, which added up to, with the same setup of 32 nodes, to 1,440 whole exomes per day. And as you know, some of you might know that the sequence cost on this is the famous $1,000. And we calculated with a cost analysis that includes everything on the compute side. There's power consumption and space and cooling and everything. We calculated that it could be accomplished, the analysis itself, for $22 per whole human genome. As a final thing, I would also like to mention that Of course, now speed is not everything, that we also have proven accuracy, and we actually have a page on that, which is given here in the bottom, QIAGENBioinformatics.com/accuracy, that it's not only a high-performant and extremely user-friendly solution, but it's also a highly accurate solution. So a comparison of results from the biomedical genomic server variant calling workflow together with the IVA, we compared with the gold standards variants from Genome in a Bottle using the GCAT portal, and the sensitivity and specificity were comparable with 97% and up to almost 100% respectively. And we also had comparison to open source pipeline with BWA and SAM tools, and the variant calling pipeline had a more than 4 times lower false positive rate, with very close to 0, and compared to 0.0 to 23%. And we also have made accuracy benchmarks on copy number variation detection, and come up with some really promising accuracy numbers. So by that, I would like to move on to Michael McManus from Intel, who is going to present some of these interesting reference architectures that we propose for different scenarios.
Thank you, Michael. I will switch slides here. Let's see. So I'm Michael McManus. I work at Intel, and I've been in the industry a while as well, just like the other Michaels. So what I'm going to talk to you today about is really about some of the systems and principles behind building those systems. So basically, I wanted to just start with a single slide review of the work that Intel has done in life sciences code optimization. So as you can see, we've worked with QIAGEN from Michael's discussion, but we've worked with the Broad, we've worked with many of the life sciences codes, dozens and dozens in genomics, and also in molecular dynamics, in cryo-electron microscopy, and computational chemistry. So Intel has made a point to work with these vendors of software to make sure that the software is fully taking advantage of Intel's CPUs. So along with that effort of optimizing code, Intel has been promoting the Scalable System Framework, which is a concept for building highly performant and scalable systems. And so basically this is addressing bottlenecks that are in the industry, well, in the computing infrastructure in the industry. So you have walls that exist between memory and storage, and you have, as I mentioned earlier on optimized software, there's a lot of these effects. And then you have a bunch of different workloads that range from high-performance computing workloads and infrastructures to big data, machine learning, visualization. A lot of these systems are not identical, and what Scalable System Framework is trying to do is show that you can build a single system that can encompass all of these different kinds of workloads. And of course, we as a company are trying to democratize this. We're trying to make HPC cover these workloads and be available to everyone. So that's a lot of the effort that's behind this Scalable System Framework. And if you think about what we're doing, I'm not sure how many out there have seen some of these slides, but if you look at today, you have on the left column, you have the traditional structure of compute with its cache. You've got memory, storage, and you've got some sort of parallel file system like Lustre. But in the future, what we're moving towards is much tighter integration. So you're getting high bandwidth memory, you're getting faster, much faster SSDs that are close to memory speed that are next to the CPU. You've got much faster SSDs for normal storage. And then you're going to basically a version of things like Lustre that have a two-tier two tiers to them. One is a burst buffer, which is a very high speed version of Lustre, but small capacity. And then underneath that, a much larger capacity version that's using spinning hard drives. So this tighter integration along with the optimized software and this whole idea of how to build scalable systems is what's enabling more performance to come out of the systems that are being designed. So a standard system that you might want to think about is basically shown here on this slide. So it's somewhat obvious, but you have compute nodes and you have the I/O nodes of what I was just speaking about, like a burst buffer kind of node. You have your fabric, whatever that could be. It could be OmniPath from Intel, it could be InfiniBand, it could be Ethernet even. Then you have nodes for logging in and managing whatever the size of the system. You may not need that for a small system. And then the parallel file system, which is typically Lustre. And then some ways to get data into and out of this system, which is typically either InfiniBand or 10 or 40 gig Ethernet. So that, and then there's also some software that you could use in larger installations, which is some cluster-ready software that Intel provides. It's open source. So, so let's just talk about sizing for a second, some of the parameters here. So if you take a look at a general schematic, this is just a rough schematic, but you'll see that you've got, on the right, you've got compute nodes, you've got fabric, you've got management, which is 1 gigabit Ethernet. And again, the fabric can be faster Ethernet, it can be InfiniBand, it can be OmniPath. And then you have storage and the login and gateway nodes. So those are the basic components. This is just in an easier to absorb schematic. So that's the idea. And if we continue on here, we'll see that, those of you who maybe don't know me, I'm a chemist, an organic chemist by training. But after doing a lot of these benchmarks, it came to me that we could consider, you know, a standard workload where you're running a number of genomes as like a chemical reaction. You could derive a rate constant that is characteristic of that particular workflow, just as a use in estimating systems. It's obviously not going to be super precise, but it is a good way to estimate how to scale your system. So you can run a genome workload, an exome workload, a gene panel workload, or an RNA-seq workload, and you can come up with constants that will help you understand how to build your system. And you can use, what I've been doing is expressing these constants as how many, for example, genomes per node per unit time. And so I'll go into that in a minute. But basically, this is the idea. You have, in this case, from FASTQ to VCF, you have an overall workflow that you can define these constants for. So there's also a storage constant that you can consider, which is like how much on a per node basis storage do I need as you're building your system. So I have some assumptions here that are just based on storing all the files for now. Obviously, the customer can do what they want, and a little bit of extra buffer to make sure there's room. But these are sort of worst case scenarios just to make sure the scale is right. So basically, what you have are for a 30x genome, you can read the numbers, but they're not insignificant numbers. I mean, 600 gigs, and much larger for 50x genomes. And these are the numbers that are used in some of the storage calculations. So, so these K values, you know, really where do they come from? As I mentioned, they come from actually running benchmarks. So basically, Michael alluded to this. We ran some 30x whole genomes. We ran 24 whole genomes in 24 hours on a 16-node cluster. This is with the Intel 2697 V3. This is the Haswell class processor. It was using Lustre, and you come up with this rate constant of 1.5 genomes per node per day, or 45 genomes per node per month. And I'll review these in a bit. You can do the same thing for exomes, which is in the white paper that Michael described earlier. And you come up with a K of 45 exomes per node per day, or 1,350 per month. And you can see the difference in scale between genomes and exomes in terms of how many you can do. And then internal benchmarks that Michael at QIAGEN team has done was to run some gene panels on a slower processor, still a Haswell processor, but a slower one. And the K for those benchmarks is, per panel, since they're small, is 175 panels per node per day, or 5,000 or so per node per month. And then finally, RNA-seq runs. And these numbers are much smaller per node because they take a lot longer to run. So you can see the numbers are not so large. So the next slide then shows some of the storage numbers, also from some benchmarks. And so basically, if you use the numbers that I showed on the slide, for like 600 gigs as the max, say, for a 30x genome, for a FASTQ and all the other files, you end up with about a 27 terabyte per node per month. And you just keep repeating this. But I will point out that if you look at the exome number here, you see that exomes accumulate storage far faster than genomes because you can process them much quicker than the ratio of the file sizes. So they accumulate very quickly. And then, of course, gene panels go pretty quickly, and it's fairly similar if you're processing a full pipeline to be similar to the storage consumption of genomes. And then finally, RNA-seq, which are slower and take, as a result, take less storage per month. So if I were to just summarize these, you can just see them here on a per month basis. So I just want to talk a second about Lustre because, you know, what is the role of Lustre? And you'll see in the right under storage type, the IEEL is actually Intel Enterprise Edition for Lustre, and NAS is network attached storage. And so Lustre gives you tremendous scalability and expandability. And as I mentioned, you can use in larger systems a two-tier system of SSDs for a burst buffer and spinning drives for a capacity tier. However, if you're just building a small system and you're going to remain small and you don't necessarily need to scale, you can consider using SSDs instead of using Lustre. It just depends on your needs. And just to be clear, SSDs are used in the burst buffer too. It's just in a different way than in a small system. And just to show you, this graph came from a white paper that HPE released recently. And it shows an alignment process using BWA. And it shows using network attached storage in the blue line. And it shows Lustre in the orange line. And as you add nodes, you can see Lustre is relatively flat, whereas the network attached storage has trouble keeping up as you add nodes. So just something to keep in mind. This shows how Lustre makes things fairly stable and performant. So let's talk about sequencers for a sec. So we talked about all these constants, and now the challenge is you got a sequencer, it's got a bunch of output, and now you know per node how many genomes you can do, how much storage it's going to take. So we have to do kind of an impedance match here and try to figure out, and I'll pick a few examples of how to line up a set of nodes with a specific sequencer. So here are all the sequencers that I showed on the prior slide, and this is a table that comes from their documents, which shows their performance on a monthly basis. And so what I did is I said, okay, here's all these monthly outputs, and I used the K values and just made the table so it showed the number of compute nodes needed to match that monthly throughput. And you'll see that the 32 nodes under the HiSeq X10 on the left is what Michael was talking about. And then the other nodes I'll explain as I go along. And then for storage, if you line the same grid up, you can see the storage on a monthly basis for each of the nodes that you need to match the output of the sequencers. So what we do is we take this information and we take an example like a gene panel example, and let's just look at the Thermo Fisher I and PGM. So it does 840 panels a month. And using those prior numbers, it really only takes one compute node, and we'll need 26 terabytes of storage for that particular 30 days. And you could do that with one, as seen here, one node. And if you use Lustre, then you have the metadata server, you have the object storage server, and then your actual storage targets, which is part of the Lustre configuration. And you can actually add, this is capable of doing 5,000 panels a month. So you can run several PGMs off of this. So you can add more nodes for compute, but you would have to add more nodes for storage to make sure you can accommodate all of the panel storage. But it's a scalable system. Now, if you go to, say, an Illumina HiSeq, one of the things that Intel recommends is you use this 4-node configuration that's in a 2U of rack space. It's a really dense nodes, and they work really well, and they're available from a variety of manufacturers. So Illumina does, this HiSeq 2500 does 900 exomes a month, but the K value for this is 1,350 exomes a month for just one node. So you could actually put this 4-node system in and just populate one node. And then as you need to expand, you can populate the other 3 nodes and add more storage. So your investment that you've made in your architecture here can be preserved. So that's 135 terabytes of storage you need. And this would accommodate, if you added another node to this so that you had 2 of the 4 nodes occupied, you could satisfy roughly 3 HiSeq 2500s this way, doing exomes. Let's see. So if we continue on for RNA-seq, the RNA-seq runs are more compute intensive, and these are using the slower chip in that benchmark, but it needs about 11 nodes, and so you would use 3 of these 4-node systems, so you have 12 nodes, but you don't need as much storage. So you can dial back the storage if you're doing just RNA-seq, for example. And then finally, well, actually not finally, if you have an Illumina HiSeq X10, this is the 32-node configuration, roughly, that Michael talked about. And you have 8 of these 4-node servers. You have Fabric, you have your login node, your gateway node, and your Lustre setup, which is, if I can annotate here, this is all Lustre. These are your compute nodes here. And then also part of Lustre is the, these areas here. So anyways, this can be scaled, and if you want to scale all this, you can try to add a second X10. And if you do that, you would go from, say, the 32 nodes to 72 nodes, and then you could handle basically 3,000 genomes a month. Actually, you can handle a bit more than that, but in general, that's 64 nodes would keep you up with 2 HiSeq X10s, but you'd have a little growth if you were to go to this kind of configuration. Now I'll talk about these systems more specifically in a minute. But basically, these are generic systems, right? I'm not specifying the OEM, in other words, the hardware vendor. I'm not being specific about what the actual storage configuration is, because it would take way too much time in this webinar to cover all of those details. But what I want people to take away from this is that if you think about your problem in terms of how many genomes or exomes or whatever entity you're running on a per day or per month basis, you can, with the right CPUs, you can actually determine very quickly how many, as an estimate, how many nodes and how much storage you need to be able to process your workload. And that hopefully we'll answer those questions. So in closing, and hopefully people can see this, so as I mentioned, the details of this were done with the Haswell processor. Now, of course, everyone may know, maybe you don't, that the Broadwell processor is out. And we haven't repeated these benchmarks yet with the Broadwell CPU. So rather than provide detailed estimates, I can just tell you that what Intel has published is that they see a performance increase between 27 and 44%. But of course, that's in general. We would have to redo these benchmarks for the specific QIAGEN workflows to actually see this. So the systems designs here, as I said, are generic. If people have an interest, like if you have a particular vendor you work with and you want to build a system, Intel and QIAGEN can work together to assist you in getting something that's designed that's specific to that hardware vendor. And with that, I think I'd like to hand it back to Michael Flensborg to wrap up.
Hi, actually, I can take it from here. This is Julianne Scheid again. I'm the moderator, and I want to thank you for that informative presentation. So before we get started on the question and answer session, I would like to remind our audience on how to submit questions. You can submit questions by typing them into the Q&A box, which can be found by clicking on the green Q&A button at the lower left of the presentation window. Ah, there's one more slide? Okay, please read that one more slide and then I'll continue.
Just a second, I need to find the slide. I would just like to round off with a little information of links, our email addresses for Michael and me, where you can find us, and in the email universe, and also mention a few resources that we have available. First of all, we have the white paper around the total cost of ownership benchmark that we made for high-seq X10 data analysis. And then I would also like to mention here that we have, in this regard, we have a blog post that is also posted with a URL here. And I would also, most importantly, like to mention that for this solution and the work we have been doing here around optimized code, there is a page on the Intel domain, and then I would also like to mention that we have, of course, a solution page for Biomedical Genomics Server that is given at the bottom of this page. And thank you for listening.
Hi, everyone, again. Sorry about that. So as I was saying, we'd just like to remind you on how to submit questions, and you can submit them by just typing them into the Q&A box, which can be found by clicking on the green Q&A button at the lower left of the presentation window. And we will try to answer as many questions as we can. So our first question, is there an API and SDK publicly available for the CLC server? And if so, how about the documentation for this?
So I think that is a question for me. This is Michael from QIAGEN. So yes, we have a very comprehensive API and SDK for the solution, and we have a whole portal around it called CLC Developer Connection. That if you Google that, then you can find it, where that contains a free SDK and also and it's free to sign up in general, and also all the documentation that is needed here. Both in terms of descriptive information, but also in terms of examples. And also we have a discussion forum that is actually quite active, where developers, those using our developer tools, can exchange information and questions.
Okay, the next question. What is the practical difference between job node scheduling and grid node scheduling?
So I think that's also a question for me. So the job node scheduling is a relatively simple job node scheduling mechanism that is built into the system. It does require a dedicated compute cluster for our solution, and that is the the biggest difference to grid scheduling, which is typically larger clusters that are shared between different applications and usages, and uses one of these third-party vendor schedulers that could be PBS Pro, Sun Grid Engine, Open Grid Engine, Oracle Grid Engine, etc. They do not require a dedicated compute cluster since they're shared between applications. So that's, as I see it, the primary differences between those two scheduling mechanisms.
Next question. Does the TCO calculation include server administration costs?
No, that's actually the only thing that is not included, and that is for the simple reason that it's almost impossible to calculate giving any estimates in general, because the salary level is very different from country to country, regional, geographies, and also that it is there's a huge difference on from compute system to compute system of how much IT effort and administration effort it contains. So that's actually the only thing that is not included.
If I have a mix of sample types, how do I make sure I buy the most appropriate hardware?
That's probably for me. Michael McManus here. Yeah, that's a good question, because most people don't just run one type of sample, they run a mix. And so if you know that exomes are the most storage consumptive, and you know genomes are the most compute intensive, you can design your system to have enough nodes for compute and to have enough storage for exomes. And so it just takes a little thinking, but you can build systems that will encompass the processing of genomes and the storage of exomes, so you know you have enough general storage for all of the different sample types that you need.
How different is the hardware from each vendor, and does that pose a challenge for building a system?
Okay, I'll take that one. Well, it's a good question. The hardware, there are some common threads. For example, if you saw at the beginning the 2U 4-node server, pretty much all of the hardware vendors have that compute server, that dense, 4 nodes in a 2U space. So that is one of the reasons I chose it, is not only for its density, but also because it's commonly available across a variety of hardware vendors. The storage part's a little trickier because the vendors have quite a variety of storage configurations. So if you're building if you're building a Lustre solution, although the high-level components are the same, you have an object storage server, you have storage targets, you have metadata servers, and things like that. Those pieces are common to Lustre, but the nodes they run on do vary. So that creates a little bit of a challenge, but it's certainly clear to us now how we would do this across a different variety of vendors. So Intel and QIAGEN can help if you have questions.
How much energy does it take to sequence a genome and do informatics?
Well, I have looked at that. Basically, it's roughly about, if you do the entire process for a whole genome, at roughly a 50x whole genome, it's about 15.5 kilowatt hours to do a genome. And that, of course, is going to depend on the CPU and the specific kind of hardware you're using outside of the CPU, and what type of storage. And if you have hard disks that are 11 watts a piece, for example, versus SSDs. So it does make a difference, but using, so as a general number, 15.5 kilowatt hours, or about 55 megajoules for those people that don't like kilowatts. But it's basically, 300-watt light bulbs for 24 hours to do the sequencing, which is about 7 kilowatt hours. And the informatics is a little more. It's about 8.2 kilowatt hours. And that's about 300-watt light bulbs and a 40-watt light bulb for 24 hours, just to give you some sort of sense. And then the interpretation piece, which is after you have the VCF, is small. It's only you know, a quarter of a kilowatt hour, which is a 10-watt light bulb for 24 hours, just to give people a visual. And so, you know, it adds up if you do a lot of genomes. In some countries, you know, energy consumption is an important issue, and so it's a good question.
Great. So if there are no more questions, I would like to once again thank Dr. McManus and Dr. Flensborg for their presentation. Do you have any final comments?
I just want to thank everyone, and if there is interest out there in constructing systems for genomics, that if you're interested in the QIAGEN pipeline, you should start with Michael, and I will assist him behind the scenes if need be in terms of any kind of hardware discussion. But thank you all.
Yeah, thank you.
Okay. So today's webcast will be available for on-demand viewing through February 2nd. You will receive an email from LabRoots alerting you when this webcast will be available for replay. We invite you to forward that announcement to your colleagues who may have missed today's live event. See you next time, and goodbye.